Good afternoon everyone, and welcome to today's worked exam answer video. Today I'm having a look at an AQA A-level mechanism question, which those of you in year 12 may have already covered or may be moving on to in the next couple of weeks. So this is one part of a question that was very synoptic in that the earlier parts of this question were focused on completely different things to what we're doing in this part of the question here, 7.6. The whole question was thinking about butan-1-ol essentially. So now we're thinking about how we can make butan-1-ol. So we are told at the top of the question that butan-1-ol can be manufactured by reacting steam with but-1-ene in the presence of the catalyst concentrated sulfuric acid. Now this actually happens in two steps, and the step that we're interested in is the but-1-ene reacting with concentrated sulfuric acid to form these two compounds here. So we've got compound W, compound X, whereby the only difference between these two compounds is where this OSO3H has been added onto the chain of 4 carbons. In compound W it's on the end carbon, and in compound X it's on one of the middle carbons. We can then turn compound W, where we have the OSO3H on the end of the chain, into the desired butan-1-ol. So we have to name and outline a mechanism to show the conversion of but-1-ene into compound W in the first part of this process. So there are options of what we can make here, as you can see, W and X, and there are certain mechanisms where this is possible depending on which specific starting material you have and which substance you're reacting it with. So elimination is another mechanism where we may get more than one product that we can form. In those mechanisms, it's important that we show the mechanism to form whichever compound they've told us to form, which in this case they've told us it's compound W. In other questions it might say the major product or the minor product, and I'll come back to that when I've outlined my mechanism. It's important to also show the product that you formed, particularly in questions where it says outline the mechanism to show the formation of the major product. Make sure you draw the major product. However, in mechanisms where there is only one product, that is not something you would need to do, and something I would potentially stay away from doing, because if you draw the product of those mechanisms and you get that wrong, you will be penalised, even if your mechanism is perfect. So that's what we're going to do here. We're going to name and outline the mechanism to show the conversion of but-1-ene into compound W in the first part of this process. Drawing compound W, less important here because they've already shown us what compound W is. Like I said, if they haven't specified what the product is, they've called it the major product or the minor product, please draw it. Now, in terms of the name of the mechanism, this is something that in part will come from rote learning the different mechanisms that are used to, in this case, convert an alkene into this intermediate structure, which we don't need to know how to name, hence they've called it compound W, and then that can be turned into butan-1-ol. So there's a lot of rote learning in terms of mechanisms and knowing, right, if I'm going from this to this, this is the mechanism that it is. So the learning part of this is knowing that this mechanism is going to be electrophilic addition. However, there is also ways in which we can get the name from the information we've been given, or if you remember what the mechanism looks like, how you can get the name from there. Alternatively, remembering the name, we can now put together the mechanism. Should we have forgotten one or more of the steps in the exam, we can get what we need to draw based on the name of the mechanism and our understanding of the word electrophile and addition. So we're starting with but-1-ene. So I'm going to start by drawing that. So we've got 4 carbons, and the 1 tells us that the double bond is between carbons 1 and 2, which I can obviously draw on this left side, or I can draw on the right side. Now, because they've put it on the right side in compound W, I'm going to put my double bond there. I could have done it at the other end, would have given us the exact same thing, but I'm going to match what they've done here. Then I'm going to put my hydrogens on. So 2 on the end carbon, 1 on that second one, and then 2 and 3 on the third and fourth respectively. Now, alkenes with their double bond, that is a region of high electron density. So in other mechanisms we use nucleophiles, where nucleophiles will be attacking whatever organic starting material we have. We're not going to have nucleophiles attacking an alkene because a nucleophile wants to donate a pair of electrons, and this already has a region of high electron density. So this alkene is going to therefore react with an electrophile, and an electrophile is an electron pair acceptor. So the electrophile is going to accept a pair of electrons from the double bond, and in the process of doing that, add on to this alkene structure. Now, we're using concentrated sulfuric acid, so we need to identify within that formula where our polar bond is for the alkene to be able to attack the delta positive atom in the sulfuric acid. So sulfuric acid has the formula H2SO4. And again, based on these structures, we can kind of figure out which bond we're going to be dealing with, because we've got a hydrogen that goes on to the second carbon, and we've got the oxygen that then joins onto here. So we're going to be using the HO bond here and here, and then the hydrogen will go onto this carbon, and the OSO3H will go here. Now, they've drawn all of this out, so again, you can draw all of this out and match what they've done, or you could do it in what is a slightly easier way and have the H and O bond shown, but then rather than drawing out the S and the double bond O's and the other OH, we can then just write SO3H like that, where the hydrogen will be delta positive and the oxygen delta negative, because oxygen's more electronegative than hydrogen. So that's the polar bond that we are exploiting, if you will. I'm going to draw it out in full because they've drawn it out in full in compound W, so I'm going to match what they've done. Either will be fine. Probably drawn this a bit big based on how much space I have left myself, but there we go. So an electrophile, an electron pair acceptor. So the double bond in my butanene, the electrons in that double bond are going to attack the delta positive hydrogen. Partial charges are not needed. Again, if you include them and get them wrong, you'll be penalised. So it's up to you if you want to put them in. I'm putting them in here for your reference now, but I probably wouldn't put them in a mechanism in an exam situation. Now, if that pair of electrons there is being used to form a bond to the hydrogen, we then need this hydrogen to break free of the rest of the electrophile. So the bond between the hydrogen and the oxygen will break, and both of those electrons will go to the oxygen. That is then going to generate an intermediate, and it's going to generate what we call a carbocation. So carbo-carbon cation, positive charge. Now, this is where it is possible to get two different products. So all I'm going to show for now is the breaking of the double bond, and then all the atoms, hydrogen atoms that were already on those carbons, I've drawn. We've now got a space here for something and here for something, and the electrons in that double bond are now being used to bond to a hydrogen, and there are two places that hydrogen can go. It can go on the second carbon from the right, or it can go on the end carbon on the right. And if the hydrogen is going in one of those two places, the rest of the electrophile is going to add on into the other position, which is why we have in compound W, H there and the OSO3H here, whereas on the right hand side we've got the H on the right and the OSO3H on the second from the right. That's why we get those different isomers being formed. Now, they haven't mentioned major or minor product in this part of this question. However, compound W is actually the minor product and compound X is the major product. And I know that based on the carbocation intermediate I'm about to draw. Now, we have to form compound W, so the hydrogen needs to go on to the second carbon from the right there, leaving the positive charge on the end carbon like that. That is a primary carbocation, and it is a primary carbocation because the carbon with the positive charge is only attached to one other carbon. So this is a primary carbocation, whereas the carbocation that would be used to make compound X, by putting the hydrogen on the end and the positive charge on this carbon, that would give me a secondary carbocation because we have a carbon either side of the one with the positive charge. And a secondary carbocation is more stable than the primary, meaning we get more of compound X from that more stable secondary carbocation than we do compound W from the less stable primary carbocation. We don't need to consider that here because we're told we're making W, but what we do need to do is make sure that we therefore put the H and the OSO3H onto the right carbons. That's our intermediate structure. We then need to draw what's left of the electrophile. So we've got the O and the S and then the two double bond O's, and again you wouldn't need to draw all of this out. You could use the OSO3H version from up there. The oxygen is going to now have one extra electron than it did before because it's taken both the electrons from that bond, so it needs to have a negative charge, and if it's then going to attack the delta positive carbon, we need to show our curly arrow coming from one of the oxygen's lone pairs, because a curly arrow can only ever start at either a lone pair or a covalent bond because it's the movement of a pair of electrons. So the final arrow we need to add here is from the lone pair and show it attacking the positive carbon on the right hand side there. And that will then generate compound W. And as I said, because they've shown us the structure of compound W, they've told us they want us to show the mechanism for forming compound W, we wouldn't need to draw that product here. Had it have said the minor product that can be formed from butanene reacting with sulfuric acid, we would need to draw what that looked like. So no marks for that here. The 5 marks, just to illustrate where they come from, you get 1 for naming the mechanism. You get 1 for this first curly arrow from the double bond to the delta positive atom in the electrophile. So that's the 2nd mark. You get another 1 for this curly arrow here to show how the electrophile essentially splits into 2. And you then get your 4th mark for getting this carbocation intermediate correct for whichever product you're meant to be drawing. So having the positive charge on the right carbon and adding the hydrogen to the right carbon. Then the 5th mark is from this curly arrow here from the lone pair on the rest of the electrophile attacking the delta positive carbon. Those are our 5 marks. Now, compared to calculations, I think these are a lot more accessible 5 marks, a bit less stressful, fewer places for mistakes to be made. Obviously that's partly my personal preference, but you can learn the mechanisms and know the curly arrows and pick up marks fairly easily. They will be really picky with your curly arrows, as I've said in other videos before, so make sure it's obvious they're coming from the bonds and where the electrons are going to in terms of pointing either at an atom or not that it's included here at a bond. Make sure you got your lone pairs on there, make sure you got your charges in the right places. Don't draw it really small. Longer bonds, easier to show accurate curly arrows. Coming back to what I said before about using the name to help us with the mechanism, if we know an electrophile is an electron pair acceptor, we know the curly arrow has to come from the alkene to the electrophile. And if we know that hydrogen only wants to be bonded to one thing, we know that this electrophile has to break open in that first step. Secondly, addition, we are adding 2 things together to make 1, which might sound like the silliest thing I've ever said on these videos, but therefore the second part of the electrophile needs to get itself onto the original structure. We can't just be adding the hydrogen and leaving the rest of it to not be attached, because that wouldn't then class as addition. We need both parts getting onto our starting alkene, and the way we can do that is to break open the double bond, because we then have two spaces, one for the H, one for the OSO3H. If we can't remember the name of the mechanism, but we know where the curly arrows can go, again, we can have a look at this mechanism and say, right, well, I'm not using a nucleophile in this first step because I haven't got something with a lone pair attacking the but1-ene. If it's not nucleophilic, the next one to go for would probably be electrophilic. Yes, this is accepting electrons from the alkene. Again, if we know that an alkene has a region of high electron density, then again, the electrophile, knowing our definition, that makes sense. Again, we can see here there's no other products, there's nothing that's being swapped off, so it's not substitution. We're not putting something on in replacing something that's already there. We're putting two new things on, nothing is leaving, there's no second product, so it can't be substitution. It also can't be elimination because we're not eliminating any atoms, so that leaves us with addition. So yes, there is a lot of learning that we can do in organic chemistry, that we need to do in organic chemistry, but we can also, if we understand what these terms mean and what those curly arrows are showing, we can figure it out from the names or the mechanisms. Hopefully that's all been clear, but as always guys, if there's anything that I've said that you're not sure about, please ask either in the comments or send me an email. I'm always very happy to help. I hope you all have a very, very lovely day, and if there's anything question-wise that you want me to look at, again, please just let me know. Thanks so much for watching. Take care.